Hey guys, Mr. Betts here. Let's take a look at a few examples where we're connecting position, velocity, and acceleration using integrals. This first example here is actually an example I used early on in the school year. And in this problem, we're given the velocity function for a vehicle, and we want to know how far that vehicle has traveled over a period of time. When I first introduced it, we found the velocity at different times, and we used those velocities to approximate how far it went. Now that we can actually evaluate definite integrals and we know how to apply that, then we can find this more exactly. So the idea here is we know that velocity is the derivative of position. So that means position is the antiderivative of velocity. So if I want to know the position at any given time, in this case at 2.3 seconds, we can take the position at the initial time and add on the distance that it's traveled. So the integral from 0 to 2.3 of the velocity with respect to time. Now, what I'm doing here would be useful. It'll tell me where the car is at a given time, but I want to be careful here. And the question says, how far does the car travel? So rather than answering this question, where is it at the end, I want to know how far it's gone. It actually turns out that if we say that it's at position 0 to begin with, these are the same answer to two different questions, but we do want to be careful that we're answering the question that's asked. So this definite integral right here gives us displacement. And the wording here, how far does the car travel, makes it sound like it's a distance traveled problem, which means we would take the absolute value. However, the velocity here is always positive. The car is never going to be going backwards during this situation. So the distance traveled and the displacement are going to be the same thing. So what we're looking for here is the value of this integral, the integral from 0 to 2.3 of the velocity, and that's going to tell us the car's displacement and also distance traveled, since the car is only going in one direction. So we're going to plug this into our calculator because this is not an integral that I would want to evaluate by hand, and it is a calculator problem. So taking advantage of our calculator, we're going to get an answer of 147. Now it doesn't say here, so I'm going to round to the nearest thousandth. By default, that's what we always want to do. So 147.512. Now, in the context of this problem, we also want to make sure we include units. So I don't know if that's 147 miles or 147 inches or 147 feet. So I need to make sure that I include units so that we know what we're talking about. Notice that in the problem we're given units. So t is measured in seconds. Velocity is measured in feet per second. So if you imagine the area problem here that we're solving, velocity is measured in feet per second. Time is measured in seconds. So when we find an area, we're going to be multiplying those units. Feet per second times seconds is going to give us feet. So during those 2.3 seconds, the car will have traveled 147 and a half feet roughly. Now I do want to point out that this velocity right here is a model. It's not the actual function that this Tesla would be, that it would follow. So the model is going to be an approximation. So it's going to be pretty close to this, but it may not be exactly right. In the second example, this time we're given the acceleration of a particle moving along the x-axis. The particle's velocity is 4 meters per second at t equals 1. We want to find the velocity at t equals 3. So we're looking for the velocity at t equals 3, so v of 3. We know the velocity at 1. And so the change in the velocity over that time interval is going to be the integral of the acceleration during that time interval. So this is going to be sine of t squared plus 1. And we know that v of 1 is 4. So we're going to plug this into our calculator. We can do this a couple of different ways. You can evaluate this definite integral on the graph by putting sine of x squared plus 1 in for y1, and then using the integrate function on your grapher to do that. You can also do it on your home screen. In the math menu, you find the integrate function. And so you can plug this whole expression in all at once if you want on your home screen, or you can evaluate the definite integral and then store that value and add 4, or evaluate the definite integral and just add 4. Lots of ways to do it. Make sure you don't do any approximating before you get a final answer. It shouldn't hurt you in this case, but it could in other examples. And so once we plug that into our calculator, we're going to get, so notice that when I did it, I included the 4 when I wrote the expression. I'm going to round it to the nearest thousandth, so 4.081. And the acceleration is in meters per second squared, and the velocity is in meters per second. So since we're getting a velocity here, the units here will be meters per second. Okay, one last example. I do want to point out this is a non-calculator example. This is a problem that is a little bit simpler with a calculator, but definitely doable without. So the idea here is we're given the velocity, and we want to find the total distance traveled by the object over some time interval. What we have to keep in mind here with total distance traveled is that we can't simply integrate the velocity from 2 to 5 because this right here gives us displacement. And so if we have any direction changes, if the object changes from moving to the right to moving to the left at some time, or from the left to the right, then this is going to be wrong because the motion in opposite directions is going to cancel each other out instead of adding. So total distance traveled, we need to integrate the absolute value of velocity. Well, in order to do that, we're going to need to know when the velocity is positive and when the velocity is negative. So the very first thing I'm going to do is I'm going to figure out here where the object is moving to the right and when it's moving to the left. And to do that, I'm going to start by factoring. So the velocity is going to be t minus 3 times t plus 1. And if I set that equal to 0, the velocity is equal to 0 at t equals 3 and t equals negative 1. So just based on that, with 3 being on the interval from 2 to 5, that makes me think that the velocity is going to change at 3, especially since this is a single root here. We're probably going to get a direction change. So just to confirm that, I'm going to make a sign chart here. And the velocity when t is 0 is going to be negative. When t is less than negative 1, velocity is going to be positive. And when t is greater than 3, the velocity is going to be positive. So what this tells me then is I'm going to need to find total distance traveled, I'm going to need to actually evaluate 2 integrals. I'm going to evaluate one integral from 2 to 3. And this distance traveled, or during that time interval, the object's going to be moving to the left. So I'm going to use the opposite of that to get the distance traveled, because remember we're using absolute value. And then from 3 to 5, I'm going to do another one. And since the object's moving to the right, that integral is just going to tell us how far it went during that time. So this is going to equal, so I'm equating to this integral right here. It's going to equal the integral from 2 to 3 of t squared minus 2t minus 3 dt. Now, that integral should be a negative value, but the distance traveled needs to be positive. So the way I'm going to handle that is just I'm going to put a negative in front. And that's going to make my negative displacement be a positive distance traveled. Now I'm going to add on the integral from 3 to 5 of the velocity. And I can evaluate those by hand. Again, this is a non-calculator problem. So this is going to be a little bit of algebra, but not too bad. So I'm going to go ahead and distribute that negative in here. So we got negative t cubed over 3 minus t squared minus 3t. All of that, sorry, that should be a plus and plus, evaluated from 2 to 3 plus t cubed over 3 minus t squared minus 3t evaluated from 3 to 5. Then we're going to plug in those values. So we get negative 27 over 3 plus 3 squared plus 3 times 3 minus negative 8 over 3 plus 2 squared plus 3 times 2 plus 5 cubed over 3 minus 5 squared minus 3 times 5 minus 3 cubed over 3 minus 3 squared minus 3 times 3. And I'm going to box that, not just because I'm out of room, but because I can. That is a numeric answer that is equivalent to my final answer. So no need to do any simplifying and possibly make a mistake along the way.